All right, let's get started. I trust everybody had a good, relaxing, pleasant weekend. I hope you're as sick and tired of these masks as I am. But there it is. I don't know if you guys follow the data that the university publishes on number of COVID cases.
Isn't it 25 now?
Oh no, it's 27. Well, 27 as of last Thursday. The newspaper just published, they claimed they had the full list, but they only published up from August. And if you go back to the last week of July, there are a couple of other cases in there. If you follow that, you'll realize that the number of cases is increasing exponentially. So it'll be interesting to see what we come up with today. In Cape Girardeau, there are 900 and some odd cases, and there was just another person died over the weekend. So this is serious stuff, and keep your mask on and social distance, and avoid the bars and parties and things of that sort. So, all right. Does everybody have access to the webpage? Has anybody not tried? If you've not tried yet, try it. Okay, and if you're not able to get in, send me an email and I will fix it. Okay? I've been pretty good about fixing those pretty quickly. What may end up happening is I have to delete you and then re-add you, so then you'll have to try and sign in all over again. All right, what we want to do today, we've done the introductory material, we've talked about natural selection. If you go to the web page, there are a couple of little shorter videos, one on Darwin's observations, one on the 4 biases and all of those sorts of things. Make sure you look at those little videos. That might be all you need rather than looking at the entire video. And I will do the same thing for this lecture. This whole lecture will be on the web page, but then I will also break out small snippets and try to explain what I think are the key points. So make sure you do that. What I want to do today is talk a little bit about biomes. I'm going to talk primarily about terrestrial biomes because that's where my interest lies. But before we can do that, we need to talk about just a few basics. You know that the planet Earth is round. How do you know the planet Earth is round? You know that it's round because of gravity, right? We had that discussion. That's why the Ozarks are small. That's why the Appalachians are small compared to the Rockies and the Sierras. That's why the Rockies and the Sierras are small compared to the Himalayas. Okay, it's because of gravity. Some mountains are brand new, so they're really tall. Other mountains are very old, so they're really short. So here's the planet Earth, and there's the axis, goes something like that. Although you understand that the Earth isn't perfectly vertical, right? It's tilted on its axis, and the Earth spins. That's sort of an interesting concept, right? Because back in biblical times, they didn't understand that the Earth was spinning. How do you know that? How do you know that they didn't understand the Earth was spinning? Well, you know that because of the descriptions that we use, right? The description that we use is that the sun rises and the sun sets. The sun doesn't rise and the sun doesn't set. The sun is a stationary object relative to the Earth. It's the Earth that is moving, okay? So when you read in the Bible that, God stopped the sun for X number of days, no. If anything, he would have stopped the rotation of the Earth, right? But no, the Earth is spinning on its axis, and that's what makes it appear as though the sun is rising and the sun is setting. Okay? So the Earth is tilted, and that has another consequence. Let's imagine here we have the sun, and this is not to scale, obviously. There's the sun, and there are the rays of the sun hitting the planet Earth. And where are they going to hit the Earth with greatest intensity?
At the equator.
At the equator. So let's just draw the equator right there. And there's an atmosphere that overlays that, okay? So the atmosphere is going to be thinnest right there at, well, not thinnest, it has equal thickness around the planet. But in terms of the distance that those rays from the sun have to traverse in order to get to the surface of the Earth, that distance is going to be shortest right there. And of course, way up here, the distance is going to be longer. Okay? So when you're up here or down here, the filtering effect of the atmosphere is going to be greater. When you're right here, the filtering effect of the atmosphere is going to be least. Okay? What that means then is that the temperature right here at the equator is going to be greater, partially because there's less filtering activity on the part of the atmosphere, but also because that's the part where you're closest to the sun. Okay? That's why it's warmer as you go south towards the equator, or if you're in the southern hemisphere, as you go north towards the equator. All right? So we have these poles, north and south. You understand that those poles are not perfectly stable, right? That those poles are moving. So the poles themselves, even though the Earth is spinning on its axis, and the axis of the Earth is tilted, you understand also that the axis of the Earth is wobbling. So it's not perfectly stationary, it's wobbling. And then in addition to that, the magnetic poles of the Earth are not perfectly stationary, they're wobbling as well in a cycle that's different from the wobbles of that regular axis. Okay? And every so often, you get what's referred to as a pole reversal. So what's north is suddenly south, and what's south is suddenly north. Okay? And then it flips back again. Those things have consequences, right? The wobble, the tilt, the wobble, and then the reversal of the poles. And you can find that reversal of the poles in the fossil record by looking at orientation of magnetic particles in the fossil record. All right, so back to this whole concept right here. We understand that this is tilted, so in reality, depending on where you are in that period when the Earth is making its annual rotation around the sun, right? The closest part to the equator might be there or it might be there, depending on where you are, okay? We're just going to keep it simple now and pretend that everything is nice and, 90-degree angles and all of that. So let's change our scale yet again, okay? Now, here comes the sun, and it's heating up everything at the atmosphere. All right? Great. So that air mass immediately over the equator is the hottest. What does hot air do?
Rises.
It rises. That's why we have hot air balloons, right? Because hot air rises. So all this air directly over the equator begins to rise. I'm going to change the scale here yet again. My apologies. My artwork is so limited. Okay? So this air now is going to begin to rise like that directly over the equator. As that air rises, what is happening at the surface? If suddenly all the air right over Cape Girardeau was started to go up, what would happen? We'd be in a vacuum, we'd all suffocate, or what? It's such a trivial, obvious question. You'd think it must be a really profound question or answer or something. It's not. It's really basic. It's really trivial. All right. We'll do the experiment at some point. I'll come into class and give everybody a straw, okay? After we're able to take these damn masks off. You're going to put that straw between your lips and you're going to suck really good. And you're going to fill your mouth with air. Is there now a vacuum in front of your straw where you sucked all the air away? No, air came in to replace it, right? Yeah, it was that simple. So as this air rises, other air has to come in to replace it, okay? So that air is coming here from the sides. That is hot air. Now, maybe your brains are addled because you've been living in southeast Missouri for so long. I know mine is. You don't think clearly, you don't think straight and all of that sort of stuff. I blame it on the humidity, okay? Why is the air here so humid? Well, a number of reasons. One, we're right there by the damn river, okay? What do you know about warm air? What does warm air do in terms of moisture?
It sucks it out.
It holds it, right? Warm air has a lot of energy, so it can hold on to a lot of moisture. So here's all this warm air, and it's holding on to all of this moisture, and the air rises. It goes up and up and up and up and up. And as it rises, what happens to the temperature of the air? The temperature drops. And as the temperature of the air drops, it has less energy, which means it can't hold on to the water. So where does the water go? It falls. Right? That's why it rains so much at the equator. Because as that warm air is rising, it's cooling. It loses the water falls back down as rain. So here's all this air coming up, it's rising, it's rising, it's rising. It's being replaced by air from down below. And now it's getting pushed and pushed and pushed, but gravity is pulling it back. So where does the air go? It goes out to the sides. Like that. Okay? And it's getting colder and colder and colder, and what happens to cold air? It sinks. So now this cold air comes down like that. And as it comes down, what does it do? It warms up. And as that cold air starts to warm up, its ability to hold moisture increases. Okay? Where does it get the moisture from? From the ground down below. So this air, this cold air, cold, dry air is falling. It's warming up. As it warms up, its ability to pick up moisture increases. And suddenly, it's sucking up all the moisture from the ground down there. And now that air hits the ground, and some of it goes that way, and some of it goes this way. So we end up with these cycles of air movement. This air is going around like that. This air is going around like that. And over here we have a similar cell, okay? It's doing the same thing. We have these cells of air rotating above the surface. But here is where you get all this dry air. There's where you get all of that dry air. Where is that? That's at about 30 degrees south and about 30 degrees north. Okay? Roughly. Hey, where are the world's deserts? Let's list some of the world's deserts. Let's make a list of all the deserts you know of. What's the first desert you can think of?
Sahara.
The Sahara? Which is at about 30 degrees. Give me another desert. The Mojave. At about 30 degrees. Give me another one. You guys don't even know your North American deserts? Really? You're just embarrassed to say something because you don't want to look like you're smart or something. Okay. starts with an S. North America, S-O-N. S-O-N-O-R-A. What's the last letter?
N.
And good job. Excellent. I'll give you a cookie sometime. All right. The Sonoran Desert. What's another one?
Are the Badlands considered a desert?
No, the Badlands are not a desert. What defines the desert?
It's like less than a certain amount of rainfall per year.
It doesn't get a lot of rainfall?
Yeah.
Yeah, that in general, that's true. The physiognomic definition of a desert is an area where the mean annual evapotranspiration exceeds the mean annual precipitation. In other words, more water is evaporating out of the stomata of the plants than is falling to the ground. Okay? So Mojave, Sonoran, Great Basin. One more in North America. Texas, Mexico, small corner from Mexico, Chihuahua. I can't even spell it. That's probably spelled incorrectly, but the Chihuahuan Desert. All right, some other worldwide. What's the desert in Israel? The Negev. What's the desert in the southern part of Africa? The Kalahari. What's the desert in Australia? The Great Victorian. All of those deserts are roughly 30 degrees north, 30 degrees south. Okay? Okay. So now you understand a little bit about those rainfall patterns. There is sort of another pattern that I want you to think about. And let's imagine we're standing on the beach in Central California. Okay? So here's the beach, and here's the coastal range, and then here's the Sierras, and then there's the Great Basin. Okay? So that you can tell you're on the beach because the waves are crashing onto the beach. Okay? Which way is the wind blowing?
Inland.
It's blowing inland. Okay? So the air is coming like this, and as that air is traveling across the beach, it has a fair bit of moisture. So now this coastal range is pretty short, right? No big deal, so the air goes over that. But now the air hits the Sierra Nevada mountains. And as that air hits the Sierra Nevada mountains, it climbs. And what happens to the temperature of the air as it climbs? It drops. And as the temperature of the air drops, its ability to hold moisture goes down. So what happens to the moisture? It falls as rain. So it's raining on the west-facing slope. All right? And now the air goes over the top of the mountain, and it begins to fall. And it's cold, dry air at the top of the mountain. And as it falls, it warms up. And as it warms up, its ability to hold moisture goes up. So it's sucking up all the moisture from the surface like that. So that's where you find the desert right there. Okay? That's dry. So when you're on, that's referred to as the rain shadow. When you're in the rain shadow, that's where you're going to find a very dry habitat. So all of the vegetation over here is getting much more precipitation than it is over here. Okay? So that's one thing that's influencing the distribution of vegetation. you ever fly in an airplane and you're flying out west, you don't see it so much here in the Midwest. All you see when you're looking down out of an airplane window in the Midwest is just these big circles, you know, from all these pivot irrigation systems. That's all you see is farmland and stuff. But when you get out west and you look down and you see these mountains, and you'll notice that one side of the mountain is really dark and the other one is really light. And that's because of the vegetation, right? So what's controlling the vegetation on those mountains? Why is one side of the mountain more lush than the other side? Well, one factor is this right here, okay? Are you in the rain shadow, yes or no? Okay, if you're in the rain shadow, then you're not going to get as much vegetation. If you're on that side where you get more rain, you're going to have more lush, thicker vegetation. All right, now on the north side versus the south side, if you're in the northern hemisphere, what's the difference in temperature between the south-facing slope and the north-facing slope? Where is it warmer? You guys know what a trough wall is? Anybody know what a trough wall is? You see it a lot out west, especially in New Mexico and Colorado and Arizona. People will build a house and then in front of the south-facing wall, they'll build a wall that has nothing but windows and then some ventilation right below it and a little bit of ventilation right above it. And they use that as an insulating mechanism. So what happens in the winter time when the angle of the sun is low, they're using the sunlight to heat up the air right in front of the wall, which then warms the house. Okay? And in the summertime, they're using it to shade the house. So they're using glass that's polarized, and in doing so, they can shade the air that's right in front of the wall and keep the wall cool. It's called a trough wall. All right, the south-facing slope is going to be warmer than the north-facing slope. Higher temperatures, less moisture, okay, than the north-facing slope. That's why in the northern hemisphere, you're lost in the woods, you find out where the moss is growing on the side of the tree. It's growing on the north side of the tree, not the south. Okay? There are these birds called cactus wrens in the Sonoran Desert. And what they do is they build their nests inside the saguaro cactus. The saguaro cactus is the cactus that looks like this when you've seen those standard, you know, sort of spaghetti westerns and whatnot. I guess spaghetti westerns wouldn't have saguaro cacti because they're all filmed in Italy. But you see a western that was filmed in the Sonoran Desert, it's those cacti that look like that. Okay? And what the cactus wren does is it puts a little hole in the side up there, excavates that hole, and that's where it makes its nest. It always makes the nest on which side of the cactus? Now, if you were a cactus wren, where would you build your nest? On the south side, east side, west side, or north side? North side. That's exactly what they do. Okay? They might be bird brains, but they're not stupid. Natural selection has favored the birds to build their nests on the north side. Okay? All right, one more little tidbit here before we move on, and that is this. So here's the slope. This is east facing, and this is west facing. Okay? And so we're not in the rain shadow anymore. We're out in the middle of the Midwest or something like that. Which slope is going to be drier? The west-facing slope or the east-facing slope? Well, let's think about it. Where does the sun, quote-unquote, rise? Rises in the east and sets in the west. So the sun comes up in the east. Okay? Okay, so here's the sun. And all this sunlight is warming up the east slope. Okay, and the west slope is in the shade. So up until about noon, the east slope is getting nice and warm. And the day is heating up. And now at noon, the sun goes over the top, and now the sun is on the west side, and the sun is warming up the west side. It's a warm day, and now in the warmest part of the day, the sun is heating up the west side. So which side is going to be drier? The east side or the west side?
What's that?
The west side. Because this side, I mean, the whole air was heating up all day long. This was in the shade in the cool morning. But now it's the hottest part of the day, and now the sun is beating down directly on you. So it's the west side which is going to be drier and hotter overall than the east side. Okay? One more little tidbit, and then we're going to move on and look at some pretty grass and stuff. Let's think about temperature. And climate change and all of that good stuff. So let's make a graph. So this axis right here is temperature. And this is time. So we're going to call this day 1. So that's 1, 1. And this is the end of the year right here. So this is 12/31. So right there is about the middle of the year, right about there. So when is, for us, when is the hottest day of the year? Roughly, basically. I mean, there's going to be a little bit of a shift, but in general, when's the hottest time of the year?
Celsius?
Yeah, so which is about right in there. That's when it's hottest. And when is it coldest? Right about there. And then right about there. So that's what temperatures look like. That's the average temperature. Okay? So we can talk about the temperature amplitude. That's the yearly temperature amplitude. Okay? That's the yearly temperature amplitude. So this is the average temperature throughout the year. I'm going to call that T bar. T bar is the average temperature. Now, depending on where you live, right, that graph might look more like that. There are some parts on the planet where the yearly temperature amplitude is really small. Okay? Other places where the yearly temperature amplitude is really high. But it's not just the yearly temperature amplitude that we care about. There's also a daily temperature amplitude. So you know that within any one day, it's coldest in the morning, and then it heats up, and then it gets cold. So the daily temperature amplitude is doing this. Okay? So we can think about that as being our daily temperature amplitude. maybe you've been paying attention, and maybe you've been reading or listening to people talk about climate change, and maybe you understand what the issue is. Maybe it's not perfectly clear to you what the whole problem with climate change is. You've certainly seen the consequences of climate change. What are the most obvious consequences of climate change for us here in the U.S.? We've experienced one event here just recently.
More severe weather.
Yeah, more severe weather. Okay. So we're getting more hurricanes, and the hurricanes have greater intensity, and they're happening more often. Okay. We're having more thunderstorms. They're greater intensity, and they're happening more often. We're getting more flood events on the Mississippi. They have greater severity, and they're happening more often. Okay? So those are the short-term immediate consequences of climate change. What's the real problem, though? People, when they first started talking about climate change, they had an unfortunate use of words. They called it global warming. And it is true that the planet is warming up. Okay? It's going to warm up maybe as much as 5 degrees centigrade in your lifetime. Okay? Which is important, right? Because already what's happened to the polar ice sheets? They're melting, right? It's now possible, and the Russians are doing this, which is good for us because they won the Cold War and we're all now Putin's puppets and so on. But now what's happening is the Russians are able to take their ships and go completely across the Arctic. It used to be totally locked in ice. Now, it sucks to be a polar bear because your habitat is disappearing. Okay? Kiss the polar bears goodbye. Probably in your lifetime, they will have gone extinct. Sorry. Oh, we'll see 1 or 2 of them at the zoo, but that's it. Okay? The other reason it's a problem is because as that polar ice cap melts, ice is white and it's reflecting back heat. So it's actually like an insulating blanket. It's reflecting heat away. Now, instead, as that ice melts, the Earth heats up, and it's going to heat up even faster. Okay? Do I care that the planet is 5 degrees warmer? I'm old, you know. So, yeah, it doesn't affect me. Sucks to be you, but it doesn't affect me. Okay? The increased temperature really isn't that much of a problem. Distributions of species are going to shift, right? Places where we used to be able to grow crops will no longer be able to support crops. Places where in the past we couldn't grow crops, we now might be able to grow crops. Things are going to be different. Lots of species are going to go extinct. We're in the middle of a mass extinction event. That's the way evolution works. Those species will be replaced by other species given enough time, right? That's called punctuated equilibrium. The system is self-correcting. After we've mucked it up, it will fix itself. The planet is fine. We don't need to save the planet. The planet will take care of itself, okay? It's a dynamic system. It will repair itself. We may or may not be part of that new system, but there it is. The real problem with climate change is not the increase in temperature. The real problem with climate change is these temperature amplitudes, and not so much the temperature amplitude, but the variance of the temperature amplitude. Okay? In other words, it used to be that that yearly temperature amplitude was really stable. Okay? But now, one year it's really small, the next year it's really big. So it's becoming more variable. The same is true for the daily temperature amplitude. One year, or one day, that temperature amplitude is really small. The next day, it's really large. Okay? So it's that increase in variability of the temperature amplitude which is the problem. It makes things unpredictable. Predictability is important for plants and animals. How does a plant know when to drop its leaves for the winter? What environmental cues does it use? All those oak trees and maples and hickories and pecans out there, how do they know when to lose their leaves in the winter? What happens if they hang on to their leaves too late? Then they don't get to reabsorb all of that energy out of the leaves, all those chemicals, and now they're at a disadvantage in the following spring. What happens if they drop their leaves too soon? Then they've missed out on growth opportunities and their reproductive output will be less in the next year. So it's an important decision. How do they do it? They base it on day length and temperature. Well, the day lengths aren't changing, but the temperatures are. So the plants are becoming less finely attuned to when the exact moment is they should begin the process of losing their leaves. The same is true in the spring, the opposite problem. When do you begin to bud out? It's primarily based on temperature. If suddenly you get a warm spell that's much too early, you begin budding out, and then you have a hard frost, you bet wrong, and you lose. Okay? I have this glorious cherry tree in my, I love cherry trees. This glorious cherry tree in my backyard, and it bet wrong this year. It budded out too early. Frost came. All the energy that it had invested in those, in the flowers and in the initial leaves was lost, and it never recovered. All right. Why do we care? Why does the farmer care? What's important to the farmer? Why is farming such a big deal here in Missouri? Well, because we have a nice long growing season. What defines the growing season? What's the definition of the growing season? When are you going to go out and start planting your corn, or your soybeans, or your milo? When are you going to start? January 1st? Get a good start, beat everybody else? No. Well, part of it's going to be when can you get into the field, depending on how muddy it is, but what else?
When the temperatures get right.
Yeah. So you have to have, right, frost-free days. So it has to be that first day when you know you're not going to get any more frost. Okay? And then you want to get all your crops in, depending on what crop it is. If it's cotton, it doesn't make that much difference. But you want to get those crops in before the first frost of fall. Okay? So it's the number of frost-free days which defines the growing season. Well, if these amplitudes, daily and seasonal, yearly temperature amplitudes are variable, that means the number of frost-free days is extremely variable and unpredictable. So suddenly for the farmer's job is now much more complicated and much riskier because he can't predict exactly when to start and when to stop. You don't know how long the growing season is going to be because of that. There were years when you could get 2, maybe 3 crops in. Now, maybe 2. Sometimes just 1. Okay? So it has a direct economic impact on the ag industry, and therefore it has a direct impact on you when you have to pay for your groceries. All right. Let's look at some pretty graphs. know it's not true, but I always feel like you just see, you don't even have to push the button, it comes on all the way itself. You just have to think about it, it comes on. All right, let's see which monitor this thing is going to pick up. There we go. All right. Let's just look at a couple of graphs. We've already talked a little bit about temperature and precipitation and seasonality and things of that sort. I'm not going to concentrate on the aquatic biomes. I know some of you are more interested in the aquatic biomes. But let's look at a graph here, and the x-axis is going to be temperature, and the way this graph is illustrated, the colder temperatures are on the right and the warmer temperatures are on the left. And then annual precipitation is on the y-axis, and when we look at habitats, well, the first thing you notice is the relationship between temperature and precipitation. Notice in areas where you have warmer temperatures, you get greater precipitation. In areas with colder temperatures, you get less precipitation, and that's simply because cold air just doesn't hold moisture, okay? But look at the different types of habitats that we can define. For example, tropical rainforests are going to be places with a lot of precipitation and relatively warm temperatures. Also, tropical habitats tend to have very small yearly temperature amplitudes. Okay? Tends to be warm in the summer. It also tends to be very warm in the winter. As you go north, up to the poles, the temperature extremes become really, really, really great. You can have 80-degree Fahrenheit days, okay? And in the winter, during the summer, and then in the winter, the temperatures can get down to, minus 50 degrees Fahrenheit. I was in Alaska once, and I was in this little cafe, and there were these two truckers that were sitting behind me, and they were making jokes about some tourist, and the tourist was complaining about how cold it was getting at night. And the one trucker says, "Good Lord, they have no idea what cold is, Let them come up here, when it's minus 40 degrees and experience real cold." Those are the sorts of temperatures where you take a breath and it just hurts to breathe, okay, because it's so cold. Those are the just a little side story. During the Second World War, I know this is nothing at all, but it's related. During the Second World War, when the Germans invaded Russia, they were trying to take Stalingrad, and there was a strategic reason for trying to take Stalingrad, but they got delayed in this effort, and they ended up fighting these battles in the winter. And the Germans lost that battle, even though they had better equipment, and they had better gear, better clothing, and all of that sort of stuff. The Germans had socks, the Russians did not. The Germans had these rifles which were finely machined and just these precision instruments, and the Russians just had these really crude sorts of rifles and stuff. And the Russians won. The Russians didn't have socks, okay? The Germans did. And it was the socks and the precision, the lack of precision, right? Or the precision that doomed the Germans. Because they're in this nasty, muddy, grimy, dirty environment, and all these German firearms were getting jammed, and they couldn't keep them clean. And the Russian firearms were so crude and rude, it didn't make any difference how much dirt was in there, they still worked. And whereas the Germans had socks, they only had one pair of socks, and they had marched all the way from Berlin or Hamburg or something on these socks, and by the time they got to Stalingrad, their socks had holes in them, right? The Russians just had rags that they would wrap their feet around. So every night they'd take the rags off, and in the morning they'd put the rags back on. They'd always wrap up their feet, so they never wore through the rags in the same place. So their feet were nice and insulated. So they had this crude gear, and they didn't have holes in the cloth that was surrounding their feet. And they were much more comfortable, and they were able to do it. And the Germans were not. Okay? Those little tiny details make a difference. At any rate, tropical rainforest, tropical seasonal forest or savanna, subtropical deserts, okay? So high temperatures, low annual precipitation. There is a place, and of course it might have changed now since I've been there, but do you guys know where the Sea of Cortez is? You guys know where Baja is? You don't know where Baja is? Baja, California? Okay, it's Mexico. You guys understand that the Southwest, we took it from Mexico, right? So we stole Texas, Arizona, New Mexico, and California from the Mexicans. Okay, you understand that. So Baja is part of Mexico. It's called Baja, California, but it's really part of Mexico. It's a peninsula that sticks down along the Pacific coast. And on the east side of that peninsula is the Sea of Cortez. And right at the north extreme of the Sea of Cortez, you come up on the beach and it's all desert. And when I was still living out west, I used to go camping down there. And right in that area, there had been no recorded rainfall in over 100 years. So not one drop of rain had fallen right there at the northern end of the Sea of Cortez in over 100 years. And yet, there's vegetation all over the place. Okay? All right, so temperate grasslands and deserts, things like the Great Basin and so on, woodlands and shrublands, those would be things like pinyon juniper forests, which are really just pinyon juniper woodlands, okay? Temperate seasonal forests, temperate rainforest, boreal forests. Boreal forests would be like the giant redwoods or the forests on the Cascades, or if you go into the Pacific Northwest, or if you go onto Prince of Wales Island in southeast Alaska, those muskeg forests, those are the sorts of places where you get these boreal forests. So low annual temperatures and not a lot of precipitation. You get some, but not too much. Okay, we can look at, now we're going to just flip these around a little bit, and now we have temperature increasing on this side and the precipitation stays the same. Let's just look at some of these, okay? Notice what happens, notice these two graphs. Let's see, blue is going to be rainfall, and then the reddish graph is going to be annual temperature. So this is just as I was illustrating before on the board. Right there's January 1st, that's the coldest time of the year. Hottest time of the year is going to be June, July, something like that, and then the temperature decreases. And then that bar right there is mean annual temperature, and then that then is the total precipitation. So you can have a scenario where the greatest precipitation coincides with the highest temperatures. You can also have a scenario where the highest temperatures coincide with the lowest amount of precipitation. Okay? And that has an influence on what sorts of vegetation are going to be able to grow there. So here's our basic illustration. Right? We have temperature, we have precipitation. Season below, precipitation on this axis, temperature on that axis, and then highlighted here, that's the growing season. So that is the time of the year between, right there, last day of freezing temperatures, then over here, first day of freezing temperatures. So that then defines the growing season. It's when that temperature is above freezing. Okay, let's look at a couple of different places. In Colombia, holy smokes. Okay, we're in a tropical rainforest. Look at the precipitation. There's no seasonality. Look at the temperature. There's no seasonality. Let's imagine you were a farmer and you are looking for a place to farm. Of those three places, where would you go? Where would you want to do your farming?
Colombia?
I'm thinking right there. Okay? It turns out to be a horrible place to do farming. Why? So we're in the tropical rainforest. Now, what do you know that's happening in the tropical rainforest right now? What's going on in the Amazon?
There's a massive fire there.
Oh, not just a massive fire, but it's been going on for years, right? I mean, the people are just burning the forest down. Why are they burning why are they burning down the tropical forest?
To farm.
Yeah, to farm. Okay, so these are subsistence farmers. The people that are doing this are, I mean, there are some big companies that are doing it illegally, but a lot of individuals, people in little villages, they're subsistence farmers. They go in and they need to grow some crops, or they need to feed their cattle or something like that. So they're burning down just a couple of acres at a time that they can then farm. And it's much easier to burn it than it is to try and clear it. It's hard work clearing it manually. Okay, so much easier to burn it. So why is it lousy farmland? Well, first of all, what's the consequence of burning down that forest? Where does most of the Earth's oxygen come from?
Photosynthesis?
And where does most of the photosynthesis on the planet take place?
In rainforests like that.
In the tropical rainforest. So as those forests are being removed, the amount of available oxygen in the atmosphere goes down. Okay? You depend on that oxygen. All the oxygen that you breathe comes from plants. So as those tropical rainforests are removed, availability of oxygen in the atmosphere decreases. Bad news, okay? So now there they are, it's just 1 acre, 2 acre, 5 acres at a time, but then there are millions of people doing it, so the amount of loss is significant, okay? So now why is that such poor place to do agriculture? It's poor agricultural soil. There's this wonderful little experiment. It wasn't an experiment, it was a business opportunity by this German. This German goes down into the tropics. He says, oh man, this soil is so rich. And he cleared all this land. I don't know how many thousands of acres he cleared. And he started growing crops. And I don't recall what crop he was growing. But he planted all these crops. And the first year, the productivity from his crops was enormous. The rate of return was just through the roof. And these German guys going, man, we're going to make a killing doing this. Nobody else has figured out that these tropical soils are amazing. So they were getting all this return on their investment. The second year, the return they got on their investment was about equal to what you would get in the Midwest. They were a little bit disappointed, but they thought, okay, next year will be good again. The third year, they got almost nothing. Why?
Lack of nutrients and stuff.
Yeah, lack of nutrients. Because there's so much rainfall that all the rainfall leaches out all of the nutrients. So it's not that they were taking the nutrients out of the soil, it's that the nutrients were being leached out of the soil by the rain. In a regular tropical forest, those nutrients are replaced all the time by trees that fall, by vegetation that dies and falls to the surface. If you go into the tropics, a tree falls down, you come back a week later, and the tree is totally decayed. Here, in the Midwest, you cut down a tree, the tree falls down, 20 years later, the tree is totally decayed. You go to Chaco Canyon, New Mexico, and go look at those cliff dwellings, and look at these ponderosa pine vigas that are in those cliff dwellings. Those things have been there for 1,200 years, and they're still perfectly solid. Okay? It's because there's no rain there. So it's all that rain, right, which is just taking all those nutrients out. There, everything rots very quickly. The rain washes it out, leaches it out. Okay? So very poor place for agriculture, and yet that's exactly what we're doing down there. We're cutting all this forest for subsistence agriculture. Those 5 acres that this peasant burns are good for a couple of years, and then he has to go find another 5 acres and do it again. So the place where he just cut down all that vegetation becomes basically a wet desert. Okay, we can look at all sorts of other places. Oh, let's look at Sitka, Alaska. Okay, so Sitka, Alaska, that's going to be this temperate rainforest up here. Temperatures, how about that, man? Just a little bit above freezing, kind of warm in the middle of the year. Okay, let's look at Omaha, Nebraska. Yikes, okay, cold, but not too cold, right? Nice and warm in the middle of the year and a fair amount of precipitation. Omaha, Nebraska is going to be a temperate scrubland, grassland sort of a habitat. Anybody here ever been through Omaha? Anyone ever driven past Omaha going north to Cedar Rapids or something in the middle of winter? And you look at that place, you're there on what is that, 25 or 35 or something, Interstate 35, you look out, you look to the west and you realize how flat it is, and you go, holy smokes, man, if the wind starts blowing here, it's going to be kind of nasty. Okay, where else? Salt Lake City, Utah. How about that, man? So Salt Lake City, Utah, temperate grassland desert. Anybody ever been to Salt Lake City? Nobody's ever been to Salt Lake City? Oh, you need to go. It's awesome. It's an amazing place. The city is amazing, especially in the downtown part of the city around the Temple Square. You know, it's so awesome. It is. It's really, the architecture is cool, and you can go into the Deseret bookstore and get yourself a magic suit, you know, get yourself some magic underwear and the magic stuff, you know, that all the Mormons wear. It's awesome. I go every time I'm up there, man. I just stop in and get myself some magic underwear and stuff. I actually have a magic Mormon suit, okay? I know I'm denigrating a particular, I don't mean it to be denigrating. I just think it's kind of culturally amusing. How's that? Okay. Let's see if there's anything else here. Holy smokes. And some of these places are sort of extreme. Notice the temperature variation isn't all that great, right? But look at the seasonality and precipitation. Just to give you an idea of the amount of variability that you can find across the planet and how much that influences the distribution of these different biomes, from these tropical rainforests, okay, to the deserts. Where are the deserts? The deserts are always at around 30 degrees, right? 30 degrees, 30 degrees, 30 degrees, 30 degrees. It's always around 30 degrees, okay? Where are the tropical habitats? The tropics tend to be equatorial. Right here, Southeast Asia, like that. There, you know, equatorial West Africa. There, Central America, okay? Let's think about equatorial West Africa. What's it like there? Well, it's tropics, okay? What is it like politically? Anybody know? really unstable. From a biologist's point of view, it is an amazing place to be. One of my former graduate students, one of my very early graduate students, a guy named Clay Corbin, did part of his PhD research in equatorial West Africa. He was working on birds. I work on flying squirrels, and there are these weird flying squirrels in equatorial West Africa called, they're not squirrels at all, but they're called squirrels. They're the anomalurids. And he's one of the few people to have seen any of these things in the field. And he wrote a small paper describing how these things move, which was kind of cool. There's a group of animals in here called Zenkerella. The genus name is Zenkerella. And it's a scaly-tailed flying squirrel that doesn't fly. If you go into museums around the world, there are only 6 specimens in museums around the world. There are 2 of them at the Cotton Powell Museum in Kent, England. The type specimen is at the British Museum. There's one, the only truly, sort of interesting specimen, unique specimen, I shouldn't say interesting, they're all interesting, but the truly unique one is in the museum in Berlin. Then there's one in Paris, France, okay? Just a handful of specimens. And there's one specimen which is just crushed, it's in really poor condition. That's all. The last time one of those animals was seen in captivity, or rather was seen, was 1932. Are they still apparent? Yeah, it turns out that not too long ago, somebody was at a bushmeat market in equatorial West Africa and took some pictures, and based on the pictures, they think there might have been a Zenkerella in the bushmeat market, okay? So, there's cool stuff in equatorial West Africa. The problem is, as a white person, going there and working, okay? Because as a white person, especially if you're from America, you're suspect, okay? People in Africa, especially this part of Africa, don't take very kindly to colonialism. And the Europeans were really big about colonialism. So the English, the French, the Belgians, okay, most of the European countries all had colonies throughout Africa. The Second World War, Hitler, he was dominating the Sahara and dominating North Africa, okay? So it's politically unstable. It's a very difficult place to get to, a very difficult place to work as a white person. When I was a grad student in New Mexico, there was this one woman who had done her dissertation research in equatorial West Africa. And she was sitting in this class right in front of me. It was a class taught by Randy Thornhill, who's the guy who wrote the book on rape, on the evolution of rape. And she was sitting right in front of me, and on the back of her neck was this little bump. And as the semester progressed, this bump got bigger and bigger and bigger. And about 4 weeks before finals, you could see this bump just moving around. It would just shift position on the back of her neck. And I tapped her on the shoulder and I go, that bump on your neck? She goes, yeah, I know, it's been bugging me. I said, it's moving, man. And she sort of freaked out, and she went to the student health center, and they sent her to the hospital. And they right away figured out it was a parasite. They didn't know how to deal with it. She went back to Africa, went to this hospital in Gabon, and there they removed this parasite. Isn't that awesome? Glad it wasn't me, but I think it's awesome. Look at Australia, man. It's all desert. Except for that little part right there and that little business up there, right? It's all desert. The Great Victorian Desert. So all those cool marsupials that you think of, right? Things like kangaroos and wallabies and echidnas and all that good stuff. That's where it is, right there. In that very thin sliver of land. Everything else is desert. That's where all the cool snakes are. That's where all the cool reptiles are, okay? That's where the Aborigines suck their toads. In Australia, the cool thing about Australia is this. Here in North America, most of the snakes that you encounter are harmless. There are only a few snakes that are venomous, right? And they're pretty easy to avoid. And there's only two snakes in North America that are truly lethal, right, that have neurotoxins. Everything else is just a hemotoxin. But in Australia, most of the snakes that you encounter are venomous, and most of the snakes that you encounter will kill you. Isn't that cool? All right, so let's just look at, just very quickly, some pictures of what these different habitats look like, right? So tropical rainforest, you can see how thick and lush the vegetation is. And these are all of the places where the biological diversity is so amazingly high. So here in the tropics, there in the tropics, there in the tropics. Madagascar is sort of a weird story. The reason it's so diverse is because of isolation, but Madagascar is also experiencing the greatest decline in number of species as a result of anthropogenic causes, right? But here, you know, in the Philippines and in Sumatra and Borneo and all of that, look at the amount of biological diversity. That's where all the biological diversity is in the tropics. And if you want to work in the tropics, it is amazingly difficult. Because most of what you care about is way up in the canopy, and those trees are big. And the only way you're going to get up into that canopy is by using cranes and stuff of that sort. It is an amazing place to be. It's a very challenging place to work. Okay? Compare that, right, with some of these savannas where you get this vegetation, and the vegetation is just sparse, right? You get a lot of understory. In the tropics, you get almost no understory, right? Everything is way up at the top. Here, everything is at the bottom, and there's very little vegetation up here at the top. Or deserts, okay? That's Choya Cactus. The common name for Choya Cactus is teddy bear cactus, because from a distance it looks like a warm, fuzzy teddy bear. In Baja, California, the primary form of vegetation is Choya Cactus. Okay? The needles, the spines on Choya Cactus have barbs, little hooks, so that when they go into the skin, you cannot pull them out. Okay? And yet, in Baja, California, as you're driving around, all these ranchers, their cattle are running free across the range. And all the cattle are emaciated. And you stop and you get closer to the cattle and you look at them, and you realize their mouths and their lips and their tongues are just impaled with the spines from the Choya Cactus. There's nothing for these guys to eat except for Choya Cactus. So these cattle are out there munching down on Choya Cactus, tolerating all these spines because they're so hungry. And they're all infected and pussy and all of that sort of stuff, and yet they continue to eat that stuff because there's nothing else out there. Choya cacti, if you ever get the opportunity to be in Baja or to be in parts of the Mojave where you can see Choya, you owe it to yourself to experience that habitat. It is really awesome stuff. And these sand dune habitats like this, you look at those sand dune habitats and you think there's nothing alive on that sand dune. And it's not true. You go look at that sand dune first thing in the morning and you'll see all these little tiny footprints all over the sand dune. And little bits of vegetation here and there, okay? The interesting thing about the sand dune is that it's shifting, it's not stationary, it's always moving. And that's why you don't see roads built through areas with sand dunes, because the roads get covered up by the sand dunes. And you look at that sand dune and you see all these footprints. In other words, there are animals all over the sand dune. And in the middle of summer, you put your hand on the surface of that sand dune and it is burning hot. I mean, you could fry eggs on that stuff. Then you take your fingers and you go down 12 inches underneath the surface of the sand, and it's 72 degrees. It's like air conditioning. And that's where all the animals are. The animals are underneath all that heat throughout the day, and at night they all come out and do their thing. All right. Douglas fir forest in the Pacific Northwest, okay? The California redwoods. Think about the California redwoods. Anybody here ever seen the redwoods? You've gone to the lumber yard, you've purchased some redwood, okay? What's so amazing about the redwoods?
They're huge.
They're huge. They are just massive trees, and they get so insanely tall. Here, as you look out across the horizon, go to Cape Rock sometime, or go downtown by the floodgate, look across the river, and look at the trees that are on the other side of the river, and you notice they're all roughly the same height. Why is that? Why aren't there some trees that are really tall and other trees that are shorter? They're all roughly the same height. Well, nope, it's because they're all planted at the same time. No. Why are they all the same height? Because they've gotten as tall as they can get. What determines how tall a tree can get?
Its root system.
Yeah, the roots. So what's happening? The roots are bringing in water. The water has to go up to the top of the tree. Okay? So what chemical process is drawing, or physical process is drawing water up to the top of the tree?
Capillary action.
Yeah, capillary action, so adhesion and cohesion. Okay, so it's because of the hydrogen bonds in the water makes that possible. Let's imagine you're at the top of towers, 12th floor, 13th floor, 12th floor. You get a straw. You're going to drop that straw down into there are two 55-gallon barrels at the bottom. And you're going to stick your straw into the one that has water, ice cold, perfect water. And you're going to suck that water up to the 12th floor. Can you do it? You say, yeah, man, I suck really good. Okay, can you suck that water up? No, you won't get it up 12 floors. Even if you put a mechanical pump on there and try and pump it up, you're not going to get it up 12 floors. Why not? Because at some point, you're the suction pulling the water up and gravity pulling the water down. That force is going to be greater than the strength of those hydrogen bonds. The hydrogen bonds are going to break, the water boils, you now have a bubble in there, and you can't pull it up any farther. That's what determines how tall those trees can get. The strength of those hydrogen bonds. That's it. And yet redwoods are about 3 times that height. How do they do it? 2 answers. 1, we really don't know. The only clue we have is this. The only place where you find redwoods is in places where there's a lot of fog. So they are in the fog belt of the Pacific Northwest. No fog, no redwoods. Okay? So the idea is that somehow, and we don't understand how, somehow these redwoods are getting moisture from the atmosphere rather than from the root system. That's the only thing we can figure out. Douglas fir forests. Why is the Pacific Northwest dominated by Douglas fir? When you go to Lowe's to buy some lumber, you're getting primarily Douglas fir. Why is that? Historically, those forests would have been dominated by all sorts of different trees. All sorts of spruce and hemlock and all kinds of different pines, lots of different species. But now in the Pacific Northwest, most of the managed forests are Douglas fir. And what they've done is when they cut trees, when they clear an area, they replant with Douglas fir. And the reason they replant with Douglas fir is because it grows fast and it grows straight. Okay? Makes great 2x4s, makes good boards. That's why they do it. Okay? Which means you can come back and you can harvest those trees in a reasonably short period of time. A mature tree in the Pacific Northwest is any tree that has a DBH, a diameter of breast height, of 9 inches. If it's got a diameter of breast height of 9 inches, they can legally harvest that tree, which is silly. Okay? So what you have in the Pacific Northwest are monocultures of Douglas fir. Everything is Douglas fir. Well, it turns out there are a couple of insect pests which love Douglas fir. If you go into British Columbia and you're standing there on the side of the road looking at these forests, the first thing that occurs to you is, man, 80% of the trees here are dead or dying. And that's true. And that's because you have a monoculture and you get these pine bark beetles or spruce budworms. They get in there and they just completely decimate the forest. And they go, oh, we love Douglas fir. So they do this one, then they do the one right next to it, and the one right next, and everything is Douglas fir, so they get them all. So now all you need is a lightning strike, whammo bammo, and everything goes up in flames. One of the reasons the fire seasons are so intense in California right now, and for the last couple of decades, is because of the fact that we're cutting all this stuff and replacing it with monocultures. That, coupled with the fact that you get this pine bark beetle infestation, and then you get some exceptionally dry periods, followed by a really wet year where all the undergrowth grows, followed by a couple of dry years where everything dies and dries out. It's just a recipe for disaster. Okay? All right. I'm going to skip through all of this sort of stuff. You can look at these images on your own. Just, I want to say one thing about that's what the Great Basin looks like. That, as an image of the Great Basin, that is probably the worst picture you will ever see of pristine. That's not pristine Great Basin habitat. What you're seeing in this illustration right here is something called cheatgrass. Cheatgrass is vegetation that was imported from China. Most of the land in the Great Basin is BLM land. BLM, I know, stands for Black Lives Matter, and they do, okay? But out west, BLM stands for the Bureau of Land Management. Most of the land out west is owned by the federal government, by you. Okay, it's the Bureau of Land Management. The nice thing about that is you get to use that land. The camp, to fish, to hike, whatever. It's open to you. It's your land. Okay? Ranchers get to use it as well to run their cattle. They pay, on average, about 75 cents a head per year to run their cattle on BLM land. Okay? So now, in order to improve the productivity of the land, because cattle don't like sagebrush very much, they planted cheatgrass. Or they introduced cheatgrass. And cheatgrass just took over the Great Basin. And it grows so thick, it displaces the sagebrush. But it turns out nothing eats cheatgrass. The mice don't eat cheatgrass. The wood rats don't eat cheatgrass. There are no amphibians or reptiles that eat the cheatgrass. The birds don't eat cheatgrass. So you've introduced all this cheatgrass, which nothing uses, not even the damn cattle like cheatgrass. So now you have this whole system dominated by cheatgrass, and you've got a biological sterile place. Nothing will use it. So now the efforts are, how do you get rid of the cheatgrass and restore the sagebrush? If you're ever in the Great Basin, you can find places where there are nice stands of sagebrush, and if you ever get to see the sagebrush, it's a thing of beauty. In the rain, it looks purple, and after it's rained, you can smell the sage. It just has this incredibly, just delicious smell to it. It's just really fantastic. All right. Oh, one more thing. You get up into the tundra. Has anyone ever been up close to the Arctic Circle? You need to try and get up towards Fairbanks. You can fly into Anchorage pretty cheap once we can fly again, right? Rent yourself a car and just get on that highway, go up to Fairbanks. Go past Denali. And as you go north, the amount of elevational change that you'll experience isn't very great. But what you're going to discover is that the trees are getting shorter and shorter and shorter and shorter and farther and farther and farther apart. Until some places you'll come to a place like this, there's a tree, there's a tree, there's a tree, and most of the trees are just these little short things. That's referred to as the taiga. So it's this tundra kind of vegetation with these short little stunted trees. Why are all the trees so short? Because the growing season is so insanely short. There's so little precipitation available to the plants, they are stunted. There's just no photosynthesis taking place. So you end up with a tree that's this tall and might be 600 years old. Okay? And that's just the extremes of temperature and lack of precipitation. Whoops. And then, of course, things like our glorious habitat here in southeast Missouri, swamps and marshes and vernal pools. Vernal pools are temporary pools. I'm going to skip all of the water stuff. We'll talk a little bit more about that later. Okay? All right, I'm going to skip all of that. Oh, one more thing. If you ask the question, where are the most productive habitats on the planet? The answer is in those sorts of salt marshes, brackish marshes and salt marshes. That's where the productivity is higher than anywhere else. That's where the most photosynthesis is taking place. That's where the most stuff is going on in the water. That's where the most soil microbes are. It is an amazing sort of habitat. If you've ever been in a salt marsh, it stinks. Okay, it stinks because of all of the decomposition. It stinks because of all of the methane production. It stinks. Okay, but as a biologist, it is an amazing sort of a system. That's where all this productivity is taking place. Okay, mangrove swamps, we'll talk more about those later, more about those aquatic systems later, and all that stuff. That's it for today, okay? Remember for lab, we're going to be outside. I'm assuming it's going to be dry. Let's plan on being outside. We'll meet here and go from here outdoors, okay? See you guys on the appropriate lab day.